Okay, we are a nonprofit internet talk series. Sometimes we have occasional coffee chats as well. We have no affiliation to any company or product outside of sponsoring our venues or food. We're monthly-ish, although we've been quite consistent in that recently. We are focused on systems programming for quite a broad definition of systems. That could be anything from networking, operating systems compilers, or databases, which often I think could be as well quite biased. We have many past talks, such as these ones, Data Talk K-Joins, Massive Accessibility, and one that is not databases in the bottom right corner, CO Notes, which is also excellent. There's a history of all the talks we have in self-based systems XYZ, and they are all meant to be recorded, but sometimes things happen. If you would like to give a talk, please scan this QR code and sign up to give a talk in any of the areas that are listed here, or maybe even a little beyond. We're always looking for more speakers, and especially at this time, it is important to mention a thank you to Gigabyte for hosting, but if you have a venue that can host 50 plus people, please let us know. We are in a position where there are not venues locked for the next couple of months, so it would be very good to have more venue options. So please let us know if you have venues available for us. Thank you. Organizers, do we want to do a promotional speech from Gigabyte?
Let's get to the professional speech. First of all, yes, thank you all for joining us this evening. It's like a pleasure to host you all. And this is the first meetup in this our new office. We just moved it like a couple of months back, and the previous ones have been in our old Sunnyvale office, so it's good to have you here. Many of you know that Gigabyte is a distributed Postgres SQL database, but I also want to point our new piece, which is like Miko. Miko is memory plus knowledge, cool name, and which helps you the multi-detic systems to kind of like really manage your conversations, your memory, extract learning, and really update the knowledge bases. So that's the whole idea behind the product. And you can join our Discord channel, and the QR codes in the back as well. So yeah, welcome again. Yeah.
All right, thanks again, Gigabyte. So today we have two talks. First from Yao Yue, the CEO at IOP Systems, on, one second, my brain goes dead whenever I speak, on caching systems. And then Eric at Databricks will present on automatic data clustering. Thank you both.
All right, thank you. First of all, I'm very impressed that Alex got my last name right. This is, I'm sure you're.
And then I forgot the topic, right? I practiced it.
No. You earn way more points for getting that right than the topic. I'll talk about the topic. Yes. Okay, so today I am going to talk about like a batch of research that was done back when I was still working at Twitter. I was not the primary author of any of these. The primary author was someone who is now a professor at Harvard, but back then he was a PhD student at CMU. And he was an intern at Twitter twice, and he was a fellow at research fellowship recipient at Meta. So I'm trying to summarize someone's 300-page PhD thesis, essentially in 30 minutes. So any omissions or biases are purely mine. All right. So again, this is a data center caching. So it's a small slice of the general scheme of caching, which is a very universal and prevalent and useful concept in systems. All right, first I want to give you the lay of the land because caching is so broad. Let's define a little bit more specifically what we are talking about today. So cache as a research discipline or topic goes all the way back to almost as old as computers. Right, so the memory hierarchy was described about the original Enya. And as sort of like the practice of putting something faster in a smaller but closer storage compared to the bigger but slower remote storage is introduced in the 60s. And cache as a term was first used in IBM Systems 360. So by any measure, it's been more than 50 years of research going on around cache. So an assumption one could possibly make is that all the low-hanging fruits, if people have been going at it for half a century, probably a lot of the low-hanging fruits have been picked, and then we're looking at increasingly specific and/or complicated designs. And one of the reasons why I give this talk is I will show you that is not the case, and there's still delightful surprises about simple and good systems to be built. Okay, so now let's go all the way back, fast forward, right? One more decade. So this is about my background mostly. So I spent the decade of the 20 teens working at Twitter, and most of the time I actually was on cache in some form. So the beginning of that tenure was marked by a lot of cache incidents, and my coworker Dan Liu and I actually did a write-up of the 12 sub-0 and sub-1 incidents, which if you're interested in how cache systems can be screwed up, this is a very good material. But there's a lot of like hard-earned lessons, right, from all these incidents. So what we learned, what was sort of hammered into me was an obsession about tail latency, an obsession about scalability, and just particular care given to observability, because those were the things that were needed either to solve or to prevent incidents. And one specific thing that will tie into the research I'm going to talk about later was we built this little observability module called command log, or klog. So what it does is very simple. It just records the requests as they come in, drop the payload because for privacy reasons and also because they're useless for our research. And we can do this very quickly if you do it right. You can do it at line rate. So basically, it is not a problem in production to log every request. So this is going to be important because that's the foundation of the data. And the second sort of element that was helpful in doing research is that I grew increasingly unsatisfied with the status quo, which was Memcached and Redis. Right, those were wonderful projects, and I read a lot of their source code, learned a lot. But one of the fundamental things I struggled with was, why do we need two projects to do something that is fundamentally one thing, which is a very fast RPC server with some key value, style, memory, storage on top, so you can retrieve data and store data. Right, so I decided we should be, and it would be possible to have a modularized design where you decouple these two things, which is the RPC server and the storage, and then that will give us more flexibility to do innovation on both sides. Right, so it's basically what you would expect if you design from first principle. Everything that has a purpose will have a name and have clear boundaries. And the end result, as related to this talk, is that it's relatively easy to plug in a new cache system on top of the RPC, so you can start using it relatively quickly. So then it gives a reason for us to seek better cache design, because we have a path of introducing those things into production instead of having to rely on upstream, right, Memcached or Redis to take in those changes, which is much harder. All right, so that's the landscape. So now we're in the 2010s. As you probably know, if you work for a company, writing paper is very low on your priority list for anything, whether your day job or even getting promoted. So we had this klog thing in 2012, 13 at the latest, and we have Pelican in 2015, 16 when we open sourced it, but I would have need to wait another almost 5 years before any of the research would start. So now let's get to the arc, right? So it's a bunch of research and they are all very closely related, and I'll tell you why. First, the who. As I said, I am just here to basically summarize the work. I didn't do most of the work. Most of the work was always done by the students at the time. So in this case, Jun Chen and Yadro were the two PhD students. And you do not need to look Chinese to work with me, by the way. This is purely Emer's fault. Emer at the bottom was their advisor when both were studying at Emory University at Vickers Point. So that's the common connection. And Emer and I went way back. Before I dropped out of Cornell, Emer was in the next office. So I've known Emer for a long time. And Katie Rashmi is Drinchon's proper advisor. So she provided a lot of help that I cannot see. I only know the part that when Drinchon showed up in the Twitter office. All right, so these are the main characters. Just keep in mind that who did the work, and yours truly is just here to convey the message. Okay, so despite not having done the work, this piece was my idea, because as soon as I got the command log, I was thinking about potentially getting all the data recorded and then shared with people who could do something about it. And part of the reason was I was reading all the papers, well, maybe not all the papers, all the relevant papers coming out of OSDI and SDI, SOSP, looking for things that I could potentially apply to my work. And it was not easy. It was very difficult to find things that were applicable, maybe beyond what Facebook was publishing in the early 2010s, because people seem to keep making different assumptions from how I view what the system needs. Right, so part of the desire is I want Twitter's data to be out there so people can build a system that would work well given Twitter's traffic pattern, and that will make it much more likely for me to benefit from the. Right, so then obviously the first step is that there needs to be data, and the data needs to be out. So this is essentially what this piece of work is. So all the labor goes into actually collecting the data. As you can imagine, it's a lot of politicking and very careful operations to collect from 200 plus clusters without anybody complaining to you. And after that, a lot of data cleaning, privacy reservation around anonymizing data, but eventually we got it out. So it's by far the largest collection of unfiltered cache traces, even to this day. So uncompressed, it's 14 terabytes of data. Compressed, it's about 2 terabytes. So lots of material to work with. It has all the things about like unique keys, as well as what kind of operations in the timestamp, but related to those operations. So by replaying the trace, you can very faithfully recreate the kind of traffic that Twitter saw in production during that time. So it turned out to be, as one would expect, it turned out to be an extremely useful data set. Even before we published the paper, Drinchon was saying, within a decade, this will be one of the most cited cache papers. And we're now at 475, according to Google Scholar. So certainly not transformer paper, but as far as systems paper goes, it's not bad. Yeah, so a lot of data, so let's look into it. So one of the first things that we noticed is just how short-lived everything is. So the cache trace actually comes with a field about TTL, so time to live. And typical TTL goes anywhere from a few minutes to maybe a couple of weeks, but almost never longer than that. And the reason is not purely because people have great heuristics saying that's the longest some data would be useful. Often the TTL is determined by something else. For example, if you cannot be sure that there won't be stale data, TTL is a very good way of bounding just how stale the data will be, right? So then you're like, okay, even if it's stale, it will be refreshed within an hour, so let's not worry about it. So it's a very convenient shortcut for engineers. The other thing is various compliance requirements. Like if you have to follow GDPR, you have to delete someone's data from everywhere in your system within a certain amount of time, right? If you have a TTL in your cache, then you largely can just point to the TTL and say, this will be gone, I don't need to do anything. So some various reasons people want to set the TTL, some of which have nothing to do with the effectiveness of cache. And nevertheless, because it's almost always set, it becomes one of the strongest design heuristics that one could use. And yet, if you look at any of the historical research, nobody treated it as such. Because historically, if you look at device cache, maybe CDN is the one exception where people set TTL. But a lot of the earlier cache research is done on systems that doesn't really have this notion of TTL. They may talk about TTL in terms of how useful data is over time, but they don't treat it as a first class, right, property of the workload. So Zcash was the first design that actually use TTL very seriously. And the way it uses TTL is it uses that to group objects. So instead of grouping objects by size, which is how Memcached does it, or you can think of grouping it by something else. If like apply machine learning, you say these objects are similar, let's put them together. There are many ways of grouping objects. Zcash decides to group things by TTL because TTL just has a very strong effect on reuse distance. So once you follow that, the second component, design decision that is consequential, is it more or less inherits the style of Memcached slabs, which is you can have a bunch of key values in one fixed size, much larger storage unit. The advantage of that is it's easier to allocate fixed sized units than if you have variable size, right? Tracking objects of variable size is a big headache. So if we assume everything is sufficiently small relative to the container size, you have this very nice bulk operation opportunity when you lay things out this way. So that's more or less the key design decision is TTL indexed groups, and groups fit into fixed sized segments. And one of the implications is that if you want to put the segments on to SSD, other than you don't want to override anything, it's actually it also would fit very well, which is something we tried. On the lookup side, this is a sort of somewhat common sense optimization. Instead of using a regular hash table, you use a hash table that has multiple slots for contiguous slots per bucket. Again, a lot of these are to reduce the number of random reads. So system optimization, honestly, cache optimization. So the end result is that we ended up with a cache system design and implementation that matches state of the art in terms of hit rate or miss rate, or slightly better because we can take advantage of TTL, but way more scalable than, say, Memcached, and also very high throughput with very low tail latency. So first piece of work. So TTL is very important. If you're thinking about designing your own, this is one of the hints. And look at TTL because it's historically underlooked. So then Finchen got sort of thinking a little more meta in the sense that when he showed up, he was very surprised that we were using essentially a combination of random eviction and recency based, and FIFO style eviction. So random, literally in the sense that if the system runs out of memory, it will just pick a random chunk, right, slab or segment, and then just kick it out. Like, we don't care if it's hot, we don't care if it's recent, we just pretty much the stupidest thing you can do possible. And then a slightly better version of that is we will say, let's just evict segments based on the allocation timestamp. So FIFO, right? So he's like, there's no reason why these super simple and somewhat stupid algorithms should work well, and yet they were at least acceptable. And the FIFO one was actually quite good compared by applying the traces we got, was actually quite good compared to a lot of the fancy algorithms, right? It's not losing to them consistently. It's actually better than some of them sometimes. So this is kind of counterintuitive and fascinating. So he was trying to understand the deeper why he would observe that. So he went out and then got even more data. So after, and in fact, after the trace release, I think we somewhat convinced Meta to release their own trace instead of just some synthetic workload, and other people also, I think, agree that, having raw data is very valuable. So the number of traces that we were able to get access grew from hundreds, which is our original data set, to thousands. So after looking at thousands of workloads and also like characterizing workload better, right? Like the how zipped in something is, or read-write ratio, or object size, or right, reuse distance analysis, all of those things, anything you can think of, probably, the folks have done it. So I'm going to skip all the actual finding path. And the conclusion is modern workloads have very short shelf life. Right? So there's a lot of things that are one-hit wonders, or otherwise used very infrequently. So very low value as far as caching them is concerned. And the other thing is the throughput is very high. So often especially if you have a very highly skewed read-write ratio, then traditional algorithms which touches every key when you read them, right? LRU will touch it, will move it to the top of the list. Things like that actually is harmful in some cases, because the pressure on memory is linear to the number of writes, and yet the number of reads is way higher, and the number of reads itself does not necessarily translate into pressure on memory or pressure to evict. Right? So there's some misalignment about the workload and the underlying mechanisms. So the hot take is, if you do the right thing, if you recognize these sort of high-level trends or high-level properties of the workloads across different segments of the industry, then it is possible to use extremely simple data structures and extremely simple building blocks like FIFO. And if you, as long as you can achieve these two properties, which is lazy promotion and quick demotion, then you can get very good results. That's the whole point of that HotOS paper. So what does lazy promotion mean? Lazy promotion essentially just means you do something about the data when you have to, as close to when you have to as you can. Which means if your cache is full, right? There's a new data item coming in. You have to do something, otherwise either you would drop the new data, which generally speaking is not a good idea, or you need to evict, right? So that's when you have to do something. So if you can defer most of the data-related operation to the moment that you have to do something, then it tends to be a good decision. Right? So what this achieves is mostly actually optimizing for the non-hit ratio related attributes of the system, such as throughput, latency, which we established earlier that in a production system we actually care. So that's one sort of high-level principle. The other one is called quick demotion. And the motivation of quick demotion is recognizing just how skewed modern workloads tend to exhibit in terms of data access frequency. So some of the anecdotes when I was looking at data was, I realized when I was operating some Twitter-related cache clusters that for one of the most important caches, you can get 60%-ish of the, so more than 50% of the hits by provisioning the cache at about 1% of the final, like the size we settled on. Right? So while this number doesn't mean too much, it is an indicator of just how skewed the access pattern is. Right? So obviously researchers know we quantified that effect with data, but that observation has held true across different workloads. So what that means is that if we can identify the long tail of objects, the long tail in terms of just, if you count frequency of access over a period of time, if we can very quickly and cheaply identify the things at the end of that, so things that are one-hit wonders or close to one-hit wonders, then we can just very efficiently reject or sort of remove this long tail from our system. And the effect of that is it just opens up so much more space for the new data that keeps coming in, right? So one of the characterization of modern computer systems is there's always new data coming in, like time series or people's online activities, right? So we're not in shortage of new data. And every batch of new data will go through the same sorting process, most of which will be one-hit wonders nobody ever looks at again, but very small slice of them will become hot. So if we have ample capacity to always be ready for the new data, then we're better off. So this is essentially what QuickToMotion achieves, is making sure you always have capacity for potentially hot future data. So if you take this design principle, and so we're saying FIFO, right? FIFO is all we need. So then logically you see, what if all I have is FIFO? How can I put FIFO queues together so I can achieve the properties I claim to be important, which is quick demotion and lazy promotion? Then sort of, we ended up with a design like this, which is called S3 FIFO. It's called S3 FIFO because it's 3 FIFO queues, number one, but also it is simple, scalable, and static. So the idea the shape of this design is actually super old. If you have heard of the design called 2Q, this almost looks identical from a layout perspective. It looks like 2Q. In 2Q, what it has is 2 queues. So a small queue and a main queue. Here we have a small FIFO and a main FIFO. Except that 2Q was, during that time, it was still believed and probably true that IRU is what you really want for your popular objects, right? So the first queue was mostly there to make it more scan resilient, but it was not ready to ditch the FIFO is all you need concept. This is ARU yet, but we're saying FIFO is all you need. So replace the ARU queue, and we also made some other changes. So there's the last FIFO queue, which is not a fully sized queue. It is a queue in the sense that it does track all the keys, but it is not a full queue that hosts actual payloads. So the value is not there, only keys. So this is the purpose of the ghost queue is there to, in some sense, measure regrets, right? I should have admitted that key instead of throwing it away. So basically we achieve lazy promotion by only doing something about the data when they get to the end of one of these queues. Right? So if you, when you insert, everybody enter into the small queue. So here the data has not been vetted, so probably a lot of one-hit wonders will be mixed in. If the key receives at least one hit, right, it will have earned the rights to be moved to the main queue. If not, then it will just be evicted, but also the label, the key will be put into the ghost queue so we can measure regret later. And that is more or less, the only other thing to note is obviously, if we regret because it would have been a hit, but it's in the ghost queue, then when we are writing that value into the cache, it gets promoted directly to the main FIFO queue. So it bypasses the new, it's not treated as a new key anymore. It's treated as something we have to see. So that is pretty much it. Right, so this design actually, when we evaluated that against, again, the data we published as well as other data we can put our hands on, pretty much outperformed any, if you look at it holistically, pretty much outperformed everything there is. And it's a very simple design. Anybody can implement it in about 50 lines of code. So it's a very good algorithm. But we're not quite done yet because we said FIFO is all you need, which I still stand by. I like it. If I'm building a web cache, I'm using FIFO for all the memory management and performance reasons. But there are still times when it makes sense to have an LRU style queue, but you can also make that better in the sense of making it accommodate modern day one-hit wonders better. And the difference is, again, we're sort of guided by the principles. We're saying, what if we try to achieve lazy promotion and quick demotion, but in LRU-like data structure, right? So some of these things will look very familiar. If you just go through the animation, you actually would understand what's happening. So first, there's a hand. The hand will keep moving to the next object whenever it is time to evict something, or whenever it sees a request coming in. So if you see a request that is hitting an existing key value that you already store, you increment the bit, or you clamp it to the highest value of the bit if it goes over, essentially marking this key as hot. Right? So that's the orange. So you remember something as being hot versus cold. That's the binary memory in the simplest setup. Now, if you have, so this is what's happening here is A is marked as hot. Now D is marked as hot. Now I comes in, I is not in the queue. You need to evict something to make space for a new object. What do? You only evict the code object. So you will sort of save anything that is hot, right? You keep scanning until you get to the next code object. Right, so the hand keeps moving and then keeps trying to turn hot objects into cold objects. So this is the recency at play. But during that time, right, during the time the hand moves all the way around from the beginning to the end, if some key has been visited again, they will become hot again. Right, so it's a bit of a race between the hand and the access. So that's the whole design, right? So you have a hand that is moving. More traffic means the hand moves faster, so it will always try to keep up with, right, the demand. But also, so basically, if you have more traffic and more insertions, then you will have a smaller time window for the traffic to warm up existing keys. So this is how it achieves the balance between eviction and new work. So this whole algorithm can be implemented in about 10 lines of code, so even less than S354, because really, literally one queue. If you don't care, right, if you're a queue. So obviously you need to be able to remove things from the middle of the queue, so it's a different implementation from FIFO. FIFO is like everything is laid out, right? I know exactly, the first to the last bit, and here you're probably looking at more of a linked list style, right, queue. So they work for different scenarios, but this wouldn't work if you need to control the memory layout tightly. But if you don't, then this is simpler and it works just as well. So it's an ARU style algorithm, but it is better than the traditional ARU for modern data. Right? I should premise by saying that. So that's the main work. I'm skipping some, but sort of that's sort of the lineage. We had data. We designed a new cache, I would say, design storage system, and then we came up with at least two very simple but effective eviction or cache management algorithms, and good for different scenarios. I think one of the things I was complaining about 10 years ago, back before all this line of research went down, was I felt people were over-indexing on miss ratio and not caring about the other systems aspect, right? But in the end, the algorithm needs to be put into a system to be useful. So let's just spell out, right? So when I worked with the researchers, I made sure they care about the things I cared about, and the net effect of that is they proposed a lot of designs that could be good for minimizing miss ratio or improving hit ratio, but was failing some of the other constraints, and therefore I said, no, you are not supposed to do that. So just me rejecting a lot of the early design was what these principles were used for. So I don't think I need to convince anybody here because most of you actually do have to build systems. So in the first group, just it needs to be able to handle load, right? So efficient use of resources, mostly CPU type resources, and needs to have high throughput and low latency, and it also needs to scale. So if you have more cores, you should be able to do more work instead of being bogged down by a universal log. And the second one is, a different type of resources, right? You need to lay down key value objects in memory, and therefore memory overhead matters, because if you have very high memory overhead, that means you store fewer objects for the same resource. That is not necessarily a win, even though, right, for the same number of objects, your hit rate is higher. So it's all like constraint based. And if you want to put things onto SSD, which will give you easily like 10x more storage, any design that has an easy time fitting onto SSD will just automatically give you so much more capacity, and therefore probably higher hit rate, even though it is worse for the same size. Right? So none of these are absolute. So, why don't we come up with designs that's good for SSD? So some of the designs I told you earlier, they were very good for SSDs, but I'm not gonna go into that today. And finally, I probably the most overlooked is completely ignored, I would say, by academia, and it even will be used against you if you propose something that's very simple, because people will be saying, what's the novelty in this? Is simplicity, right? And everybody can understand in 30 seconds. Generality, like you don't need to pick a different thing for every different scenario you run into. And if you cannot have generality, at least you should be able to have configurability, so you can adapt the design to the scenario. So we work a little bit like sort of this two-part loop where very brilliant researchers will come up with designs, and my job is there, and then go down this list and then say, how many of these boxes have you violated? If it's more than maybe one or two, then that's probably a no-go, right? And it could be a bit of a frustrating experience, but like poets say, constraints are liberating, right? So if you can short circuit all of the bad design early on, then you eventually will find some gem. And then if they take all the boxes, that's really the best kind of research one can do. Of course, the constraints has to be real, which is why going all the way back, we need to have data. So I think one of the things I think really need to preach is that improving real systems is always multi-constraint, multi-objective. So anytime we find ourselves only optimizing for one thing or even two things, then there's a very good chance we're missing something. So we should go back and ask, do we understand what the system is and what does it need? So now some takeaways. So over the course, so all this research, starting from 2020 when our first publication came out, so that's like research done in 2019, to I guess the last publication of this batch, which is like 2023, 2024-ish. Let's call it 5 years, right? So over this multi-year, I think sort of the gradient, sort of the direction that the research was going was starting from data and then starting from some kind of design that often in the beginning is a little bit more complicated, but over time just trying to do reduction, taking away all the things that we didn't feel were essential, and then coming up with simpler and simpler designs. And one of the things that people don't ask, again, if your job is to publish paper and then graduating within 3 years of publishing that paper, then it doesn't really matter too much what happens to the paper afterwards, right? But if similar is true for engineers. If you launch a system and then you get a promotion, who cares if 2 years later that causes incidents? But if we were to, in the ideal world, one would care, right? One would care, say, the point of my research is to be adopted. The point of my system is to stay online. So if those are my success criteria, then what would allow me to be more successful? Through those lens, really, you need two things, and then both things are equally important, right? It needs to be better to give people a reason to do something. You also need it to be simpler, or as simple as you can make it, while still keep it better, so people have fewer reasons to say no. And you see the thing listed here. I'm not going to read through this list, but the sort of the vibe is they got a lot of attention, a lot of adoption, and then people were talking about it because people could understand it. You do not see, for example, Setcache on this list because Setcache, in comparison, is much more complicated and therefore takes way more effort to implement. Well, I did a version of implementation, someone else did a version of implementation, but very few people would actually go all the way and implement them. And there's a big difference between simpler design versus more complex design. So, and especially when it comes to research or academia, I would say I wouldn't want to use complex implementation coming out of academia anyway. No offense to anybody who is a current student, I just don't trust your code. So what's the point of doing a complex design and badly done complex implementation? Instead of having some idea that's simple, probably with limitations, which is fine, but the idea actually is easily spreadable because people can understand it, right? And then I can adapt the idea to a complex system that I'm building if it's applicable. So in this case, S350 got turned into one way of designing or implementing Setcache. So now Setcache also has the concept of a small queue and a large queue. Right? So it's not exactly S350, but it's a very easy adaptation. So that kind of research I think is valuable because if people can understand it, they can also adapt it. And the other thing that I think everybody here, I hope you will have the opportunity to do, regardless of the role you play in this, is to do sort of a run like ours. If you're in industry, you probably have some really, really precious data that can inspire a lot of students instead of watching them making the wrong assumption and wasting 2 years implementing complex solutions for the wrong assumption, right? That's just a tragic waste of human intelligence. So to the extent possible, get the data out so people have some truth to ground their thinking and to validate their assumption, to check their results every step of the way. And then this is and on the other hand, right, like, Britain academics is how we got all these new designs. I would never have the time or even the capability to come up with all of this by myself. Right? So there's a true opportunity for academia industry collaboration. And you're starting to see some of that in a lot of the AI systems, right? If you look at the paper from ATC, from NSDI, well, ATC is no more, but NSDI, OSDI, so it's SP from the past few years. The system scale is so large, it is almost impossible for academia to entirely come up with even toy, right, setups on their own. So they're now flying blind unless they can work with someone in the industry. And this is a moment that is particularly important, I think, to encourage this type of collaboration. And a lot of the best papers I've read from the past few years actually came out of China. And that is because apparently somehow this pattern is extremely popular in China. If you look at the paper, Mooncake or whatever, you just look at the author list. Half of them have affiliation with some university, and half of them have affiliation with some companies, and a few of them have both, right? So this is working, and I see no reason why everybody should start doing it. There's no reason not to. Or maybe you need to convince someone who is higher up in your engineering organization, but I'm not here to solve that problem. Right? I'm just saying you should try. And I think this is a repeatable process. I think I've been to enough poster sessions that I know people are absolutely doing wonderful creations with the wrong assumptions. So if you can correct that, they will be making wonderful designs with the right assumptions. So lots of opportunities to do great work here. So that's it. And as I said, I skipped something. So these are the more complicated designs, which I personally am not that big of a fan of. So, but if you care, I will put the slides online, and then you can read all the things, including things that worked on less well, and then you can see why some things are more successful than others. Happy to answer questions.
Yes. Excellent presentation.
So
Thank
maybe
you.
for the sake of time, we
Yeah.
should do questions after.
Oh, yeah,
Uh,
sorry,
since we
I
have
went
another
way over.
presenter.
I did
Ah,
not.
okay, okay,
I
okay.
did not realize.
No, no problem. I thought you finished.
We
Yeah,
have
we
another
have
speaker.
we have another wonderful presentation.
No, I'm leaving, so I need to ask the question now because I'm not gonna attend the second presentation.
I'll talk to you offline.
Maybe if I link it in or something. So, see you.
Thank you. Thank you.
Round of applause, please. All right, up next we have Eric from Databricks with automatic data clustering.
Recording in progress.
Okay. Hey everyone, I'm Eric. I'm from the Autobricks team at Databricks. I'm here to tell you about AutoLiquid, which is our autonomic data layout optimization for the Databricks layout. So we're also going to present this at BLDB later this year, so you can think of this kind of like a preview talk or rough draft. Yeah, so many people worked on this, including my team and others. A bit about me. So I'm currently TL for the ML systems team at Databricks. Previously, I was TL for the radio distributed system where I worked on at Nscale and during my PhD at UC Berkeley. Before I did my PhD, I also worked on a bunch of systems at Databricks and Google, where I learned a lot. So this talk is going to have three pieces. Basically, I want to first overview table layout strategies in case you're not familiar with them. I'll talk about why autonomous data layout is a hard problem and then how we resolve it with the AutoLiquid system. So I think one thing I want to flag right off is that we're interested in full autonomy with AutoLiquid. So there are actually many systems out there that suggest data layouts but do not actually apply them. We actually want to automatically apply them, which turns out to be a much harder problem. There's some background. I think I should start with table partitioning. Just a show of hands, how many of you are familiar with table partitioning? A few of you. How many of you are familiar with liquid clustering? Okay. So it's good. I'll go into this. So this is table partitioning. It's kind of like the really basic way we organize, data in these cloud lake houses. So the goal really is to allow data skipping. Right? You want your queries to read only the subsets of your tables I really care about, and not scan everything. So in this example, we have our data organized into years, and then further something organized into directories by like customer ID. Right? So the idea is if you have a query like this, where I want to scan for data with customer ID and CDE, and in the year 2022, I can only read a subset of this data, right? So I just need to read these three directories, and I guess I only need to read two files. One was empty in this directory. Right? So there are some downsides of table partitioning. One that you might have noticed already is it's very rigid. You have this like grid layout, and then the files have to be sorted into one of these grids. So you end up with very tiny files in some cases, and then some directories have like very big files, right? Those big diamonds. So ideally, you want something more fluid, right? So you're kind of adapt your data layout so that the files are more evenly sized, and that's kind of the idea of liquid clustering in Databricks. So it's a data layout based on KD trees, which are very general. So you have multi-dimensional splits, so you can kind of split the data to produce even file sizes. And you can get the very same data skipping with liquid clustering. So for that example query, for example, liquid clustering would just read that one KD tree cell, and it actually read less files, only read one file, which was bigger, so that's more efficient. Right? So this is partly how Databricks is trying to solve the data layout problem with liquid clustering. And you can create a liquid clustering table by create table cluster by, etc. Actually, I think this is even open source, so you can do it. And And that creates a data layout like this, right? So this part was kind of before my time. It was already a project that existed, was widely adopted by Databricks, but there's still a remaining problem, right? So with liquid clustering, you still have to choose the columns to cluster by, and how you query your table. So as an engineer, you kind of have to figure out what tables will benefit from liquid clustering, what are the best clustering columns for this table, what are my query patterns change, and it's not terribly hard to figure out. Like with the previous example, your customer ID. But if you have like many thousands of tables or requirements change, it can become like a very large burden. So that's the kind of product we're trying to offer here. Which adds this cluster by auto syntax to automatically manage the data layout. Okay, so why is this hard? You might think the hard problem is choosing good clustering columns, right? Like given a workload, what do you choose, right? There's like many hundreds of academic papers on this, and including some very recent ones here. For example, like BigQuery had some blog on how to do this. And actually, I asked Gemini yesterday, like, given telemetry traces, can you give me an algorithm to choose clustering columns? I came up with something actually pretty good. I think if I gave it more context, it would have worked. But the point here is that like this part is not the hard part. There are a few systems actually in the industry that actually do this completely autonomously, and it turns out there are a few reasons for this. So the first reason we ran into was this whole asymmetry of risk thing. So let's say you build a great algorithm, it's like 80% good. So you evaluate it, it's like, hey, we would save you many customers millions of dollars. It works most of the time, etc. But sometimes you get it wrong, right? The result, customers are very unhappy with this, right? They get paged for some jobs that slow down, they say, hey, turn off this auto thing, it's doing some crazy thing, right? And the reason for this is really performance regressions are treated as critical, and cost improvements are nice to have. You've noticed that I think the budget departments will notice in the long term. That's good for customers, good for us, but short term regressions are worse, right? And what causes some of these regressions are kind of the challenges for estimation. So really estimating the selectivity of your predicates, like the pruning power of the predicates, is really critical for choosing good clustering columns. But it's a much harder problem than you might think. If you look at workload telemetry, you end up with predicates like this, like A and B or C and D. And it's very actually hard to disentangle the individual column selectivities from this telemetry. And you end up with things like data skew, so you can't estimate them accurately, and then you have filter predicates that may or may not touch a small amount of data. It's just very hard to tell from if you're just looking at the queries. And you have also end up with issues with data correlations. Like you see a lot of queries on sales date or return date. You might think it's a good idea to cluster by both, but it turns out they're correlated. So basically, doing this is actually bad. It reduces the pruning power of your data layout, right? And these issues don't show up in benchmarks. They only show up in prompt because the benchmark data often is very uniform. Finally, workloads change over time. You have new POCs, new business requirements. So your system has to adapt to these changes. But also it has to do it in kind of a measured way. It can't really overreact, right? You don't want to churn between different data layouts that will also cause problems. So kind of the frame of the problem is not choosing good data columns, it's choosing good columns reliably and adaptively. Okay, so how do we actually do this? I think the system is actually pretty straightforward once we dive into it, but there's quite a few pieces. First, we have to collect telemetry. We identify candidate columns, and then we introduce this thing we call a verification job that actually does back testing for verifying that we made correct decisions. And then we have components that handle the kind of state change complexity and feedback loops to kind of learn from these verification jobs. And the working example I'm going to actually go through is this. Say you have this table sales with order date, return date, customer ID, country. Of course, it's an auto table. And then we have several types of queries. So it's a scan over sales on order date, one on scan on return date and country. And the third one is a little bit more interesting. It's a join query using customer ID as the join key. So at a high level, AutoLiquid works like this. We have two components in architecture, one which runs in a control plane. So this is like your typical replicated service. Its responsibility is ingesting the telemetry, coming up with good candidates, and then ranking the candidates that we consider. Then the second part of the system runs in the data plane. This is the part that actually does the verification thing I talked about before, and actually responsible for applying the data layout changes. So telemetry collection is Databricks, we collect telemetry on all the queries on your table. We keep a sample of all the queries, relevant queries for AutoLiquid, about 1,000 scans over 30 days, and this includes the number and size of the files you read, the predicate columns, and any dynamic filtering expressions from joins. So for that example I had before, we store the order date predicate, this return date and country scan predicate, and actually we store this kind of interesting in-list predicate that's a dynamic filtering predicate generated by the join. So one kind of challenge here is this telemetry can contain very sensitive customer data. What we actually do is we store this in customer storage, not in our accounts. So this kind of overview. The control plane stores the high-level metadata and then references to the sensitive telemetry that's in the customer account. Okay, so the next stage is candidate identification. So we have an advisor that it's kind of like a cron job that loops all the tables on an hourly basis. And for every table, we try to compute a benefit model for all these candidates. And the model is actually fairly simple. It's kind of how you imagine. We look at the frequency of how columns are used in scans, the selectivity of the column in the scan, and then how many columns of the table we're reading in the scan, right? So basically at the end, we're trying to compute this notion of benefits, and our unit or benefit is a number of full table scans saved, right? So for example, a benefit of 1 would mean we save 1 full table scan. A benefit of 10, we save 10 scans. And the goal here is a rough ranking of these clustering candidates. So to make this concrete, remember those three scan predicates we had before. Here I'm computing the benefit for all of them. So you see for the system decided there were these 4 candidates combinations. So order date, return date, we think maybe it would say 1.8 scans. So that's our first rank, and so on and so forth. And then we also compare against the natural layout of the table. Okay? What the table is currently sitting at, just based on ingest order and what the benefit of that is. The next part is we verify all these clustering candidates. So it's kind of a division of responsibility. So we have the benefit model for rough ranking. The verification job computes the precise benefit scores. And how the verification process works is we send basically the telemetry to the collected from the advisor. We send it to a serverless background job that runs actually in the customer's data plane. And then we sample data and builds these what-if KD trees for backtesting scans. And I think I have a diagram for this. Yeah. So basically how this job verification job works is we actually sample data from the source table we're trying to compute layout. And based on the candidates, we build what-if KD tree structures. So we build k-dimensional trees for layout, kind of simulate the layout for each different table. And then we actually backtest all the scans we've collected and compute the benefit that we would have gone had we chosen that candidate, right? And this thing is actually fairly accurate because we use the same KD tree code that we actually use in prod for computing the benefits. So you can see we did experiment with some benchmarks. The actual file scanned versus predicted file scans for a number of, for instance, TP-CDS queries. You see the trend line is very, very close. So we consider this fairly reliable. And to give you an idea of what can happen when you run this verification job, here's that same example. The estimated benefits from before, but then use this verified benefit column. So you can see some interesting things. First, order date, return date. The verified benefit was actually lower than what we estimated. And this is probably because those two were correlated. Order date, you order an item, you probably return it soon after, so they're very close temporal locality.
Order date customer ID actually got boosted a lot in ranking. This is because we can get very precise selectivity estimates from the replay. Before they were, probably underestimating the selectivity. So that the second one turns out to be the final ranking. So that's our starred candidate. So in this case, what happens after we find a good candidate? What we do is we actually issue the data layout operation. We alter table, we cluster that table immediately, and then we trigger an optimized job to change the data layout of the table. One important thing is that we actually also send the results of this job back to the control plane so that we can adjust future heuristic estimates. So why is that important? Oh, I had this slide. So, and by the way, this works pretty well. So we ran a study to figure out how many cases this verifier job saves us from regressing. So if we relied on the heuristic, actually in 37% of the time, we would actually do worse than what the customer chose. I mean, it's not necessary to say we would have regressed the workload, but it was worse than what the customer would have chosen by themselves. But for AutoLiquid, we are basically we can make autonomous selections that are better than what the customer chose 97% of the time. Okay, so back to that feedback. Why do we need to deal with that? So the reason is you get more telemetry, right? The workload changes over time. Now you have new benefits. So let's say, very simple example, the number of scans we receive have increased in frequency 10x. So right, so the benefit is simply scaled from 1.8 to 18 and so on. But now you have a problem again, right? The second candidate, which we know is the best, is no longer the top ranked. How do we know if this is correct? So what we actually do is we take that feedback and we do a very simple adjustment of the benefits. We shift and scale. You can think of it like a little bit of one-step learning, so that if we apply the shift and scale then the new benefit with feedback kind of preserves the learnings from the verification job. You see that the second candidate is once again our top ranked candidate. Finally, I want to talk about the table state changes. So what happens when your workload changes, right? So AutoLiquid also manages this automatically. And we kind of have a very simple algorithm, kind of like that manages. And there's basically based on two thresholds. It's first is the obvious one, like of course we don't change the clustering unless we have a better option. That's a relative threshold. And the second one is a kind of a damping or exponential threshold, where we try to avoid oscillations by being more conservative over time. So how does the relative threshold work? Let's say we have the current clustering over time, and the benefit is relatively steady. Let's say green is this new up-and-coming candidate. We can observe it, and it accumulates benefit over time. And at some point, it's going to cross the line and become better than our current candidate. And the threshold, relative threshold is the same. Of course, we have to be a little bit better before we switch. Exponential benefit is a little bit more interesting. It's the threshold for that ramps up more than basically the more times this table has changed its layout in the past. So kind of intuitively, a table gets older as it's seeing more data or more changes. We try to be more conservative about what qualifies for a useful change. So if a table is very volatile, it'll quickly ramp changes, and the threshold for this change will get higher. So here's an example of how this works in real life. So here's a table. On the top, we show the pruning rate of the table. On the bottom, we show the workload. And the workload is colored by different colors. So you can see AutoLiquid makes a selection quite quickly in the beginning. It improves the pruning rate a little bit. After it learns a bit more, it makes a second selection, which quite significantly improves the pruning rate. But then it waits a while the workload is very volatile, and after a couple of weeks, it makes a final selection that really fine-tunes the workload. I'll skip some of these slides because I think it's a little bit in the weeds, but I think we also manage some details about liquid clustering regarding its incrementality. So liquid cluster actually supports incrementally changing data layout. as opposed to, having to force recluster your entire table at once, which helps. And we also manage that in our system. We also handle some edge cases for write-heavy tables, like online cost of writes. But this is interesting. I think one challenge actually we had as a team for a long time was, how do we know how well our selection algorithm is working? Right? We don't have benchmarks. The benchmarks just say we're 100%. How do we measure this? Right? So what we ended up doing was this thing we call shadow candidate verification, which we actually sample human managed tables. And what we do is we run our algorithm on these human managed tables and see how well we would have done on this. So we ran actually our algorithm on 10,000 random Databricks tables that, like, the only criteria, they were large enough to be interesting and they were active. So these are active tables. And we plotted the expert benefit chosen by the customer versus the auto liquid benefit chosen by the algorithm. And we found that actually the vast majority of times, like, auto liquid did better. And we looked at the reasons why. It's actually super interesting. Sometimes the people were actually, kind of too good about their workload. So they actually tried to fine tune their table for all the work they knew about, but actually reduce pruning power a lot for the table. So it was kind of not accounting for these kind of deficiencies in the system. And sometimes people were just optimizing for the wrong workloads, right? There's actually the keys they chose were only relevant for a very small portion of the queries. Because there was, like, in the very large portions that you kind of didn't know about. Right? That's actually very common. And there are some cases where we did worse. We're trying to improve those. Those tend to be on tables with very, very complex workloads, where since we spend a limited amount of compute trying to find the best data layout, we sometimes miss some. So just to recap, basically the system works with kind of two phases. There's a fast control plane loop that tries to come up with rough candidates. There's a kind of very detailed and conservative job that runs in the data plane to verify candidates. And the feedback between these two systems is what makes auto liquid work. And these are some reception numbers. So today you have to opt into the system, but we've got 13% organic adoption, 2,000 active customers. I think around 3 million auto tables have been enabled. And I think our estimates, we've kind of saved customers like 10,000 petabytes per year. And we're, of course, trying to make this better. This kind of asynchronous nature of, clustering in the background, as you can imagine, might cause frustration from customers. They're trying to make that a little bit easier, especially for these like POCs where they're trying to do benchmarks. We're always trying to improve the quality of the algorithm and improve diagnostics for customers. And of course, if you guys are Databricks customers, please try it out. Let us know how it goes. That's all I have.
So speakers will be around for questions. I presume, unless you guys have a plane to catch or anything. But thank you again to both of our excellent speakers.